we can generalize the way that we solve equations with power functions, that is, by using the root properties, to solve equations involving rational exponents, using the following facts. First, if x is an expression that represents a positive real number, so we're restricting ourselves to positive real numbers now, then if we take x to some rational power and then raise that to the reciprocal power, we get our original expression back. We get the original value back. And that's true, that's an equivalence. That's true no matter what any variables in x represent. We know that that's true because if all of the powers and roots are defined, and whenever we take an even power and then an even root, we're just dealing with a positive number, x to the p over q raised to the power q over p is x to the power p over q times q over p. But when we multiply a fraction by its reciprocal, we just get 1, so we just get x back. We need to be a little bit concerned when our base is a negative number, and we'll deal with that in a little while. But as long as our base is a positive number, we don't need to worry. So again, we're restricting ourselves to positive numbers. But if p and q are both odd, we don't need to worry about signs. We only need to worry about signs if one of p or q is even. Because then at some point we're taking an even root, at some point we're taking an even power. And we can't take even roots of negative numbers. When we take even powers of negative numbers, we get a positive result, which means that we can't recover our original negative number. Now, a second fact is that as long as, again, our expressions are representing positive numbers, if we take an equation x equals y, and we raise each side to the p over q power, we get an equivalent equation. When p and q are both odd, then we don't need to worry about negatives. If one of p or q is even, we need to keep in mind that both sides of our equation have to be positive. We'll use these facts to solve equations involving rational exponents in the following way. So here we have some example equations for which we'd like to find just the positive solutions for now. We're only interested in positive solutions because we'd like to get the basic move down before we start thinking about our worries about even roots and even powers and negative signs. So if we have x to the 2/3 equals 9, and we're only interested in positive numbers, so we're assuming that x is positive, of course 9 is positive, we can take the 3/2 power of both sides. And so x to the 2/3 to the 3/2, that just gives us x back. And then 9 to the 3/2, well, that's the square root of 9 to the third. So x is 3 to the third, x is 27. This next equation, we have x to the 3/4, but it's not isolated. In order to solve this equation, we need to get x to the 3/4 by itself. So we'll start by dividing both sides by 3. We have x to the 3/4 equals 81 divided by 3 is 27. And then we'll take the 4/3 power of both sides. So we have x to the 3/4 to the 4/3 is 27 to the 4/3. X is 27 to the 4/3. At this point, I'm going to start putting these rational powers just into the calculator, at least if they give me a nice number. And in this case, 27 to the power 4/3 just gives me 81. So x equals 27 was the solution I got in the first one. X equals 81 was the solution in the second. Notice all positive numbers. Third equation, I have x plus 1 in parentheses, all to the 3/5 equals 8. My 3/5 power is isolated. There's complicated stuff happening inside here, but I need to eliminate that 3/5 power before I can deal with it. So I'll say x plus 1 to the 3/5 power, all raised to the 5/3 power, equals 8 to the 5/3 power. So x plus 1 equals, according to the calculator, 32. Subtract 1 from both sides. Our solution is x equals 31. As long as we're only interested in the positive solutions to these equations, everything is completely straightforward. We take the reciprocal of the exponent, and we take that power on both sides.